Hi to everyone, and thanks for attending. What I would like to present today are our initial results or preliminary results on what we can learn from the lab when we're looking at hydraulic fracturing in the shale rock. But before really going to the details of the results that we have been obtaining for the past year and a half in the lab, what I would like is to give an overview of what is the NSERC energy simulation research program in the fundamental rock physics and rock mechanics at the University of Toronto. So the overall idea for this research program is really to use a combination of rock mechanics, rock physics, and geophysics to study the response to fracking by reservoir rock. So the current research work has been proposed and divided in 3 concurrent axes. One is, the first one is looking at understanding what is the role of microstructures and stress condition on coupled processes. And the past talk, we just saw an example of how important is the microstructure and also the stress state when we try to fracture our reservoir, our rock. The second axis that we're looking at is really trying to link physical processes to the elastic and viscoelastic seismic models that are used to investigate our subsurface generally in the field. And the third axis is trying to really combine what we learn from the first 2, and especially from the lab, and try to see how we can upscale those behaviors, those fundamental understanding to the reservoir scale. Overall, our really long-term objective is to impact industry, to help industry, and to create a robust strategy for the development of the next generation couple multi-scale geomechanics for modeling technology that will enable industry to better implement and operate fracking operation in both hydrocarbon, but also other energy systems, such as the geothermal system, better understanding how the CCS system will work under injection and pressure. So that said, what we need to understand is really we generally work with a natural rock. So natural rock, natural reservoirs are fractures and have a complex fabric. So, for example, if we look at the outcrop of the Montney shale, these pictures were taken in Alberta. What we see is that we can notice open fracture, closed fracture, incipient fractures, and bedding planes. So those features that really have been created in the rock during the deposition of the sediments at the beginning of basically during for shale marine environment, at least for the Montney shale. So what we want to do is actually take this rock and bring that rock in the lab, bring that rock in the lab at the same stress condition or similar stress condition as those that the rock experiences in the reservoir at depth. At that point, what we are planning is really to hydraulically fractures in those controlled conditions and to understand how the fluid that we are injecting the rock will interact with that particular complex system. And what we want is really to understand how the rock behaves and how we can best use this learning to improve our field operations. So what we are doing is getting a cube, putting this in a polyaxial machine. And polyaxial machines are quite unique loading devices that, as I said, they allow us to apply 3 independent stress states along the 3 principal directions. And that will allow us to really reproduce the stress state that the cube, cube of rock would experience at depth. And then by creating a small hole and using a mini packer, we are able to inject fluid in the center of our cube and really reproduce what that small elementary volume of rock would experience during an hydraulic fracturing operation in the field. And what we are going to do is to record the pressure response that of the injection. And what we can is actually rebuild the pressure data that generally are recording during completion. In doing that, we can start identifying what is the fracture initiation, the fracture propagation pressure, and once that we stop injecting, we can see how the rock will respond, what is the shut-in pressure, and of course, reproduce what is the excess pressure and the close pressure of that particular sample would experience. So what we did, so we create a lab, we take a sample, we recreate a block, and this block specifically for the first test that we are going to look at as a clear bedding planes, and those bedding planes are oriented parallel to the sigma 1, sigma 2 plane, sigma 3 planes, with the sigma 2 that is the vertical stress that is horizontal. The injection is mimicked along the sigma 3 directions, and that is also that will be the horizontal horizon in the reservoir. So what we did, we start injecting at a constant flow rate of about 7 milliliters per minute. That flow rate has been chosen because it mimics the pressure ramp up that a well would experience, a rock around a well would experience during reservoir injection, the reservoir scales. And what we recorded is the pressure response of the rock. So we saw that we have quite steep pressure ramp up once the cavity has been filled. We have a breakdown pressure, a drop in pressure, a pressure recovery, and then basically sort of a unstable fracture propagation process that has sort of an average pressure propagation. This is not really a stable propagation. There's a lot of drops at the rock that our pressure sensor capture. So this is quite similar to what you would see in the field as overall shape of the curve. So as we by studying geomechanics, we know that when we inject the fluid in the rock, we expect if we reach we overcome the strength of the rock, or the tensile strength of the rock, we'll be able to propagate a fracture. And that fracture, of course, will overcome the stress state. So the minimum principal stress. So the fracture will propagate along a plane that is perpendicular to our sigma 3 and is going to be parallel to the sigma 1, sigma 2 plane. In this case, is pictures here in blue plane. So, however, what we noticed in the lab was actually that the fluid was exiting our cube not along this plane, but along the green plane. That is, that means that the opening was the plane, the fracture was not developing, opening the sigma 3, overcoming the sigma 3 stress, but actually it was overcoming the sigma 2 stress. So, but sigma 2 stress was that plane, sigma 1, sigma 3, along which the failure was happening, was parallel to the orientation of the bedding planes of that particular sample. I was quite puzzled. We were not really sure what was going on at the time. So during the test, we were not just measuring the pressure response of our sample, but we were also looking at the displacement response. And looking at sigma 1, sigma 3 plane, that is the plane along which opening was happening, we clearly see that that is also parallel to the bedding plane orientation, that we could clearly see that all our displacement sensors were recording an opening, and that was actually resulting in a residual opening at the end of the pumping. So this was quite consistent with the observation from the fluid outlet that we were, they recorded at the fluid outlet. So the sides that were where the water was coming out of the cube. So looking at a different direction, what we noticed was actually something even more puzzling on the data, that specifically to the sigma 3, sigma 1, sigma 2 plane, so the plane that was along the axis of the injection, what we noticed was that one capton only was responding was recording closure along the closure of the rock. It means that there was a sort of apparent reduction in volume in that particular location. And what I would like you to note is that there are actually two jumps in the closure. The first jump was associated with the breakdown pressure, and the second was associated with the following drop in pressure that was recorded by our fluid pressure captors. So what to do? Well, at that point, there was a lot of interesting results that were not really easily explainable. So what we did, we took the sample out and we started looking at what could have happened. So, and here in blue, what we can see, the area where the our displacement sensor was showing a reduction in volume with an expansion along this axis. So what was decided was to look at all at the sample under the microscope, and that show us very interesting results. So what we saw that the injection hole that is placed on the face number 2 of the cube clearly picture fractures that were parallel to the bedding planes that were starting at the injection hole. But on the bottom side of this image, what was noticed that this fracture was actually not developing in a single plane, on a single plane, but we're creating a sort of an echelon fracture system that is clearly suggests some shear process that took place on that particular area of the samples and could lead to the impression of a reduction in volume due to the shear displacement, the local displacement. So the first, I would say, result or observation is that this type of fracture of failure during a simple injection is not a simple planar fracture. And the fracture method that's generated is not really extremely simple. So the next step is has been to decide to look at try to map the in 3D fracture networks within the cube. So on a different cube, what we decided to do that was tested in a similar way was to try to map the internal structure of the fractures. So what we did was, first of all, we CT scan the entire cube. We compare that with a previously X-ray CT scan provided on by, in this case, our collaborator Petronas, on the full core to just to make sure that the sample was to understand exactly where the natural fracture were, and then by knowing the internal fracture, what we decided to do was to apply destructive methodology that was developed by Lee and Maxipok within our group was applied. The idea was to apply 3D serial section reconstruction. That is a destructive methodology that will slice our cube sequentially, and after every slide, a picture is taken, and by putting all those sections together, it's possible to reconstruct the fracture network that is present in the cube in our sample at much higher resolution than what would have been possible to achieve with the current X-ray CT for the volume that we are looking at, that is a cube of 8 centimeters side. So by doing that, it was possible to create a high resolution fracture map that could have been used to quantitatively evaluate the response of our cube to hydraulic fracture. What was clearly evident was that the bedding planes dominate the volume of the fracture. And the new hydraulic fractures are much less in volume and are thinner than the other fractures. And so what we see is that basically of the map fracture, about 61% of the open fractures are bedding planes. The 28% really are the pre-existing natural fracture. Only 11% of the total fractures are the hydraulic fractures that have been generated by the injection. That means that apparently for our test in the lab, the new hydraulic fractures function as a connection to the bedding planes, and by connecting and allowing fluids to activate those bedding planes really are key to create a large volume of interconnected fluid path. And that's really what we think it happened. So furthermore, what we could look is to verify and validate what this observation in a quantitative way by looking at what is the spatial variation of fracture volume and aperture. And we could see that the presence of activated bedding planes were really matching the presence of these were actually activated, where the connection with the wellbore through the newly generated hydraulic fractures was created. So in this particular image, you can see that, for example, the open bedding plane were mainly above the injected well, where very little was activated on the lower. And this is coincident with this particular propagation of hydraulic fracture generated during the injections of the in brown in this image. So the other thing that we could quantitatively evaluate was really the fracture volume and the average fracture aperture that would allow us to provide some quantitative relationship, or to evaluate what is really the sort of the stimulated volume with respect to the tested volume. And the fracture aperture is, and the average fracture aperture that we measure is an important result, because it's going to be potentially key input for our future numerical models. Furthermore, by being able to clearly digitize our surface, we could start looking at aspects like or parameters like the fracture roughness. And what we noticed is that the natural fracture roughness is definitely rougher than the roughness of bedding planes. That suggests that the bedding planes are smoother, and they might tend to slip easier than the natural fracture, but at the same time, their self-propping capacity would be lower than the natural fracture one. So to conclude, what we observed from this study is that the fracture system observed in our hydraulic fracture experiments are not simple bi-wing planar fracture, as most of hydraulic fracture models assume based on simple stress analysis. Opening of bedding planes seems to be a key process during hydraulic fracturing that is not well captured in current commercial softwares. And that really leads us to state that the raw fabric anisotropy must be considered when modeling the injection process. And the way natural fractures, bedding planes, and hydraulic-driven fractures contribute to the stimulated reservoir volume is greatly influenced by the rock strength and the local in situ stress state. So what? Well, the rock strength and fabric anisotropy, and specifically for shale, the bedding planes, is critical and often overlooked in understanding how the reservoir will fracture during hydraulic fracture operations. So accounting for rock anisotropy could lead to hydraulic fracture optimization, such as pumping rates, cycles, efficiency, and so on. And accounting for bedding planes opening can not only help to improve hydraulic fracture modeling, but can also allow for a more reliable estimation of the stimulated reservoir volume, the SRV, and recovery factors, which are critical for the evaluation research and ultimately for the development plan. So that said, I really would like to acknowledge our sponsor, NSERC, Energy Simulation, Geomeccanica, CMG, Showcore, Petronas. And I would like also to make to acknowledge the students and all the students and the research associate actually work on this particular research. And in particular, I would like to mention the work of Ali Abdelaziz, Mei Li, Earl Maxipok, and Johnson Ha, that really, I would say, did the hard part of the work that I have the opportunity to present today. That said, I'm ready to answer any question you might have. Thank you.
Thank you, Dr. Grasselli. There's a couple of questions. First one is by Dr. Eldon Jafar. For the pressure response, is the pressure obtained for steady state controlled by the rate you selected?
Yes. So we were using a constant injection rate of for the test we show is 7 milliliters per minute, and the pressure response was measured at the inlet, basically almost at the downhole response. The sensor was at the injection point.
Okay. Second question by Dr. Iraj Ershagi from the University of Southern California. Great experimental work. Are you able to also measure what stress level it takes to heal these fractures?
I'm not sure what you mean exactly as a heal this fracture. To fully close the fracture, potentially yes, in the sense that it's not something we have done, but I don't see any problem. It's just a matter of designing the experiments for.
Okay. Question from Doug Beringer. Very nice results. Matches many of the field observations. Do you have any size scaling relationships to go from lab scale to field for strengths and apertures?
Okay, thank you for the question, because actually allows me to advertise what we are planning to do. So right now, the answer is not yet. The work I've been presenting is just the initial stage of a much larger project that is greatly supported by partners. I would like really to acknowledge their support. So the overall idea is to really develop an upscale methodology. Right now, we have been realizing laboratory experiments in cube of 8 centimeters. As I'm speaking, there are 2 large blocks that are almost about 1 cubic meter of Montney rock that are traveling from Alberta to Ontario, that will be used to actually test the response of our rock at that larger volume. Furthermore, we have planned to expand the same type of experiments at even larger volume of rock, about 15 to 15 by 215 meters, by collaboration with the University of Calgary. So my answer is not yet. Stay tuned. I hope that I will be able to report within 1 or 2 years results that would allow me to specifically answer to your question.
Okay. Time's up for the Q&A here. There are a few more questions on the Q&A section, so please type in your answers for all to see. Once again, thank you very much, Dr. Grasselli.